Hi, hello everyone. Today I will show you a document about how to fine-tune a CV task. I will follow the outline. First one is task analysis. What is fine-tuning? Why we need to fine-tune? How to fine-tune? Some precautions. Firstly, we all know that nowadays most of CV tasks do not need training a model from scratch, since the base model is very powerful. For example, we have a new task about face mask detection. Just during the pandemic, we all know that the face mask is very important for people. So we need to make a detection to detect whether the people is wearing face mask. Okay, I will show you a demo. Okay, this is a guy who wearing a face mask. Okay, if we have his picture, we will press the button, determine if we're wearing a face mask. Okay, the output is 1, so it means he is wearing a face mask. Okay, I will change another one. Okay, this one, determine, okay, 1. And change another one. Oh, this one haven't been determined. Okay. I will change a large one, a large picture. Very large picture. Maybe this one. Okay, this one is a very large picture. I will press the determine. Okay, yes. Means she is wearing a face mask. Okay, I will change without mask. Okay, this girl. Okay, without a mask. Okay, change another one. This boy without a face mask. So I know that we have a very good model. This model can detect whether the people is wearing a face mask. But what is fine-tuning? Okay, fine-tuning means make small adjustment to something in order to achieve the best or desired performance. So we all know that the base model is pre-trained by large data. It's very powerful, but it's not very suitable for our specific task. So we need to do some adjustment, okay, just adjustment with a small data to fine-tuning the model, fine-tuning the model to fit our downstream tasks. Okay, let us do a test. We can change the model to the base model, not the fine-tuning the model. Okay, we just change it to the base model. Okay, not use the fine-tuning the model. Let's restart the service. Okay, see? Okay, now the data is the same, the picture is the same, but the model is different. Also, we press the determine. This model determine that the people is wearing a face mask, but it's not. Okay, we change another one. Look at this one. This people is wearing face mask. It's correct. Okay, change one. Also, it can know this people is wearing a face mask. Oh, she is wearing a face mask, but the model cannot determine it. So we can see that the base model is very powerful, but it's not very suited for our current downstream tasks. So we need to do some fine-tuning to fine-tuning the base model to fit our new tasks. Okay. So just we talk about the base model basically is trained by ImageNet. It's a very big data set, maybe hundreds of thousands of pictures. Also, the base model can learn a lot from the data. They can learn lots and lots of things, lots of features from the data. But our downstream tasks, we only have a small data set, not a large public data set. So we need to use the ability of the base model. We need to transfer it to the new tasks, but we need to change the the full connection layers. Okay, this layer means full connection layers, means classification layers. We need to change the classification layers to our specified tasks to output my downstream results. Okay. So how to fine tune it? Since we have a small data set, not a very big one, so we need to transfer the ability, the ability from the cover, from the CNN layers, and we change the classification layer to our new task. This one can classify 1,000 type, but we only need a few. Okay, there are some cautions, some precautions we need to know. The first one is data analysis. We need to analyze our data, even if it's small data. Okay. Another one, we need to choose a very good, very suitable base model. It's very important. Another one is we need to set very good hyperparameters, since the parameters can determine whether the new model is outfitting, or overfitting, or balanced. Okay, let's start with the demo. Okay. In the demo, we know that we have a small number of pictures. We need to detect whether a people is wearing a face mask. So we need to do some data analysis. Okay, firstly, we need to view what the picture like. Okay, we can write down some functions like this one. We can resize the picture to 256, and then we append 10 pictures for a line, for a grid, and show the pictures. Okay, so we can show the data from the training dictionary. No, the training directory. Okay, training and the mask directory. Okay, we can show 50 to 100 picture. We can see that there were 50 pictures. All of the picture, the people wear different face mask. Okay. Also, we can show the picture from the without mask dictionary directory. Okay, we can see that all of the people haven't wear a face mask. Also, we can grab pictures from the validate mask directory. Okay, we can see that in the validate dataset, most of the people wear face masks. But we can see that the face mask is not the reality. It's just a fake picture, you know. People add the fake face mask to the people's face, you know. Not all of them are the realities. Okay. Okay, the next one we see the pictures from the valid without mask directory. Also, we can find that most of people are not wearing a face mask. Okay, this is our data analysis. From the data analysis, we can know that we have maybe 600 plus 600 pictures in the valid dataset. We also have 1,000, more than 1,000, and more than 1,000 pictures from the training dataset. So we can create the standard dataset. We can put the pictures path to the data frame and another row named target. Target one means wearing a face mask. Target 0 means on masks. Okay. The same way, in the valid dataset, target 1 means wearing a face mask. Target 0 means without mask. Okay, and then we merge the two. We merge the two training dataset and merge another two valid dataset to dataset training and dataset valid. Okay, we can show the value counts. In the value counts of training dataset, we can find that target 1 have more than 1,000, target 0 have more than 1,000. Okay. Also, in the validate dataset, there were more than 600 target 1 and more than 600 target 0. Okay, and then we save these two dataset to a CSV file. So we can use it in the training process. Okay, the next one, we can use some clustering algorithm to analyze the data again. Firstly, we need to extract features from the pictures. We create a small dataset class named lim dataset. In this class, we can get the item by open the pictures and transfer it to the tensor, to PyTorch tensor, and also get the target from the data set. And also we create a data loader, just load the data batch by batch. Each batch is 64. And okay, we then use the ResNet model to extract the features just we talked about last time. Okay, the ResNet's last layer is fully connection. In this feature, in this scenario, we change the fully connection to identity. Okay. To extract the features from the picture, and then we input the picture into the model and get the feature, and then append the feature to features, and then we stack the feature. Okay. The process of extract features may spend 2 minutes. It's very fast since we are not so many data. Okay. The shape of the feature is 520. Okay. Since we have got the features of the picture, then we can use the UMap, function to reduce the dimension from 512 to 2 dimension, and then we can plot it to the chart. Okay. In the chart, we can find that there are different colors. There are deep blue plot, deep blue dots. And also there are shaped blue dots. Okay, but in the chart, we cannot find a special pattern. We can find a special pattern, just random. So we can find that the data is random. Okay. Okay, the next one, we can use the k-means clustering to cluster the data. Okay, we search from 2 to 20. Okay. From the search, we can find that there are obvious elbow point, maybe it's nearly 15 to 20. Okay, so we assume that the elbow point is 13. So we do the k-means again with the cluster number cluster of 13. Okay, then we will show the result of the clustering with the first 50 picture. Okay. We can show the first file type of cluster. Okay, you can see that in this type of cluster, maybe most of the picture are very clear, and the face mask is very shallow. Okay, it's nearly white. Okay, you can see that, but let me check. But maybe most of the face mark is faked. It's not the reality. Okay. Oh, we can see that in other category, the color of the picture may be more clear, maybe more colorful. Okay. And another type, okay, the picture is more dark. Okay. The next one, we can find that most of the face mark is blue. Okay. The next one is more dark. Maybe most of the Facebook is darker. Okay. Also, we can use the dbScan cluster. The dbScan cluster use the two-dimension data. The two-dimension data is reduced by the UMAP. Okay. We feed the clustering, and we display the first two type. This one in this type we can find that most of the face marks is white. Okay. Okay, this one is very similar. This one is very similar. Okay, we can see that the training data is very colorful. It's very different. Okay, but basically we know that the data is okay through the different the pictures. Maybe we can train a very good model. Okay, the second one, we need to choosing a base model. How to choosing a base model is a very important phase in fine-tuning a model. Basically, in the CV task, we use the TIM, T-I-M-M. We use the TIM library to create models. So in the document of the TIM, we can find a table. Okay, let me show. Yes, we can find a table. In this table, there were many models ordered by the top 1 accuracy, top 5 accuracy, parameter count, and something. Okay, we can see that the most accuracy model, nearly 90% top 1 accuracy. But the parameter count is very high. It's nearly 300 megabits. We all know that when the parameter count is higher, then we need a very powerful GPU to train it. Otherwise, maybe it will be very difficult. But then for our course, I want to train the model in our PC, not use any GPU. So we cannot use so big parameter counts. So in this time, we want to use the ResNet. Okay, so we can search the file with ResNet. You know, ResNet, the top 1 accuracy of ResNet, nearly 85, is very similar to the top models. So I think our task is just only a binary classifier task, binary classification task. So I think that ResNet 1.8 is okay. So the top 1 accuracy of the ResNet 1.8 is 73. I think it's okay. The most important is that the parameter count is only 11 megabytes. It's very small. It's very suitable for us to train on my personal PC. For my Mac OS, it's very good. Okay, so we use this one. We use this model. We copy the name of the model to be my base model. Okay, in this TIM library, we can use the pre-trained parameters. So we all know that in the base model there are many parameters and weights are trained very good, are pre-trained very good. So we can use the pre-trained parameters. Also, we change the classified number to 2. We only need the new model to detect whether the people is wearing or not wearing face masks. Okay, we can see the structure of the model. We can see the last layer. The last layer is a fully connection layer. It's a linear layer. The input features is 512, but the output feature is only 2. Is followed by our setting. Okay, so I think that this model is very suitable for us. Okay. So the next one, we need to get the configuration of the model portrayed. Okay, we can use the model then portrayed for configuration. We can see that the information of the portrayed configuration, okay, including the tag, the input size, the crop model, and something. The most important thing for us is to get the data configuration. We use the teams, the library teams data to get the data configuration. Okay, we can see that if we want to use the base model, we need to follow the data configuration. So we need to transfer it to transform. Okay, we can use the create transform with the data configuration. Okay, we can see that it's a composed of resize, center crop, to tensor normalize. Okay, so this one we can reuse in our training process. Also, we can check the parameters count of the model. Okay, we can use the profile function. We can fake input and input to the profile function. Then we can get the parameters. Okay, the parameters less than 11 megabytes. It's very small. It's very good. Okay. So another one precautions is about the learning rate. It's about hyperparameters. We all know that the learning rate is very important for us to train a very good model. So we mimic a very simple model, just only layer named linear from 2 to 1, and we set some parameters, just max learning rate and epochs and steps, 10 epochs, and each epoch have 100 steps. Okay, we also create a optimizer using Adam, and also we need to create a schedule to schedule a 1 cycle learning rate. Okay, this learning rate have a very good curve, Okay, in this curve we can show the curve. Okay, we can show the curve by input the fake date, input which is by use the epoch and stack to step it to append the learning rate in the optimizer, and then plot it. From the picture, from the chart, we can find that firstly there was a very lower learning rate, and then warm up to the max learning rate, and then decay to a very lower learning rate. Since that our base model is pre-trained very good. So firstly, we need to use a very lower learning rate to let the model to learn some new information, and then warm up to max learning rate. With the max learning rate, the model can learn a lot from the new tasks dataset and converge, and nearly converge. Then, with the learning rate decayed to a very lower learning rate, the model can learn a lot from the new dataset. Okay. So that's hyper parameters of the training. So next one, let me check the training process. In the training process, okay, firstly we can set the seeds, set all the seeds just random, numpy random, touch, and all of the seeds. Okay, and then we check the device, check the CPU core and something. Okay, the next one we read the data from CSV. We just stored it. Okay, then we set the hyper parameters with the tag, with the number of classify, and the number of epoch, and the batch size, and something. Okay. The most important is the max learning rate, drop rate, and the weight decay, and EMA alpha. Okay. So just same like the propelled file. We also need to create our own dataset. It's a very easier dataset. And then we create the transformer. In this case, the transformer is very important, since we have a small dataset that transform the dataset to different manner. We can let the model to learn more information from the pictures. Okay. So next one, we create the train data loader to load the data from the dataset with the batch size. Okay. Okay. The next one is valid load data. Okay. Load data for data valid. Okay. Another one is EMA update, and then is training function. Training function is very important. Okay, since we can do some epoch. In this file we do 5 epochs. Every epoch we need to recount the matrix, just like loss, accuracy, the same thing. Firstly, we switch the model to train model, and then we get data from the train model or train loader batch by batch. Okay, for each batch of data, we get the input and the target. Okay, we input the data to the model and get the output, and then we calculate the loss between output and the target. Also, we can calculate the accuracy of the output, and then do some backward and update the weights of the model. Also update the learning rate. In this area, we record some metrics for later analysis. Okay, each 10 step we will each 100 step or 10 step we will print the metric data. Okay, each 5,000 step we will save the model, save the checkpoint to hard disk. Okay. In the validate function, maybe it's nearly similar with the train function. We just set the model to evaluate and no grad. Okay. Also, we get data from the valid loader, batch by batch, send the input to the model to get the outputs. And also calculate the loss between output and the target. Also calculate the accuracy, and then print the process. And also return the metric access. Okay, that's the base function. In this area, we create the model with the ResNet. Use his pre-trained weights. Also, if we have trained the model for some epochs and we need to continue the trade, we can load the state dictionary. But this time we have the checkpoint, so we just go down. Okay, we knew the since it's a binary classification, so we use the cross entropy loss. It's very normal. Okay, and also we use we create a optimizer, use the AdamW. In the AdamW, we use the learning rate of this one, and the weight decay set it before. Also, we use the learning rate scheduler to do some very good curve learning rate. This is some hyper parameters to set the learning rate. Okay, now we begin to training. For each epoch, we print the number of the epoch, and we do some trade to trade through the trade function. Also, we do some validate through the valid function. If the valid accuracy is better than the best accuracy, we will save the model, save the checkpoint to hard disk. Okay, and that's the training process. Okay, we can use this one to start the training process, just like Python train to start the training process. Since we have finished the process, maybe I think that in my computer the process may be nearly 1 hour. Let me check. Nearly 1 hour, maybe more than 1 hour. Okay. Here is the result of the training. We can find that the accuracy is keep up and up. Okay. The learning rate is a very beautiful curve. Okay. The loss, we can see that it's keep down and down. It's very beautiful. Okay. So after we training the data, we can get the different checkpoint. Okay. We can see that the accuracy in the valid date from 47 to 78 to 88 to 19 to 92 it's keep up. Okay. So we can go to the info, the program of info. In the program info, we also use the basic model and load the state dictionary saved by the training process. Okay. So you can see that we create the basic model, and then we load the state dictionary, and then we get a picture, and then we get a picture from the web UI, and transfer it to tensor, and add a batch, then import it to the model and get the output. Also, the output will do a softmax to get the probability, and then through the argmax we get the type, which one is 0, which one is 1. 0 means not wearing face mask, and 1 it means wearing. Okay. Okay, now we can see the main program. The main program is just let me see. It's just a web GUI. Just a web GUI. Use a Gradle. Okay. We can see that there are three blocks. First one is image blocks. Through the image box, we can get the file path. The second one is a button. Click the button, click the button, we can call the function of info. Input is the file path. Output to the info output. The info output is the text box. We can output the result of the info. Okay. In the info function, we call the info picture from the info Python. This one, info picture. Okay. The info picture will get the image path, and then load the path and transfer it to tensor, and then send to the model, get the output, get the probability, get the predict. Okay, let me check again. Okay, we will open the we will run the main Python. Oh, I have run another one. I will close this one. Change the port to 1. Okay. We pick a picture. We all know that this one in the valid mask is a mask. Have face mask. Okay. We can press the determine. Okay, it's very good. It's determined that these people have wearing face masks with the probability of 60%. Okay. And then we change one. I change to this one. Okay. Oh, that's wrong. So we can see that the model is not perfect. Okay, it's just let me see how much. Just 92%. The accuracy is 92. It's not 100%. Okay. So we change another one. Okay. Determine also is not 1. Okay. So we need to continue to do some training for very good result. Okay. This one is 1. Okay. So this is our demo about how to fine-tuning CV task. Let us review it. Okay. Okay, we know that the pre-training model is very powerful with very large data, but our downstream data is use very small data set, so we need to adjustment something to achieve the best or desired performance. Okay. So how to do the fine-tuning? We just change the fully connection layer to our task, and then use the small data set to retraining, to fine-tuning the whole model. Okay. So this is the process of our fine-tuning. Okay, wish you all have wish you all learn something about it. Okay, thank you very much. See you later.